will be looking at Pearson's Edexcel Combined Science, Paper 2 Physics. The paper we're going to be going through is from the year 2018, and it's incredibly important that if you want to improve your grades, that we go through the whole paper, because if you can gain a couple of marks on every single question, you will go up a whole grade. For question 1, a student uses apparatus in figure 1. To determine the specific heat capacity of water. So we can see that the equipment is set up with a joule meter, an immersion heater, a thermometer, a polystyrene cup with water in it, and a power supply to 12 volts. We've got to state the measurements needed to calculate the specific heat capacity of water. So first of all, we would want to take the mass of the water, and we would do this by taking the mass of the polystyrene cup, then pouring the water into the cup, and then measuring the mass of the plastic cup with the water in it. And if we subtract the mass of the plastic cup, we have the mass of the water. We would then take the temperature of the water at the start of the investigation, and then again at the end. And what this would mean is we're able to work out a temperature change. We would need to take a measurement from the joule meter so that we know how much energy is supplied. State 2 ways in which the apparatus could be adapted to improve the procedure. So the first thing that we could do is we could add a lid to the water to stop any heat being lost to the surroundings. We could put insulation around the polystyrene cup, or we could use a digital thermometer. Any of those answers would be correct. In part B, we are told that the student decides to measure the temperature of the water every minute while it is being heated. Figure 2 shows a graph of the student's results. So we have the time in temperature, and then we have the temperature in degrees Celsius. And we've got that shown in the graph. Predict the temperature of the water if the heating continues up to 8 minutes. So when we go up to 8 minutes, we can see that the temperature in degrees Celsius has gone to 100 degrees Celsius already, and water boils at 100 degrees Celsius, so it's not going to go above that at 8 minutes. Another student decides to melt some ice. The student melts 380 grams of ice at 0 degrees Celsius. The specific heat of fusion of ice is 3.34 times 10 to the power of 5 joules per kilogram. Calculate the thermal energy needed to melt the ice, and select an equation from the list of equations at the end of the paper. And if you look at the list of equations at the end of the paper, we would be using Q equals mL, Q being the specific latent heat, Q being the thermal energy needed to melt the ice, M being the mass in kilograms, and L being the specific latent heat of fusion, which in this case is 3.34 times 10 to the power of 5. So if we input our numbers, now we have to change the mass into kilograms, so that would be 380 divided by 1,000, and then we multiply that by 3.34 times 10 to the power of 5. And if we calculate that out, we would have an answer of 1.27 times 10 to the power of 5. A cyclist is riding a bicycle at a steady velocity of 12 meters per second. The cyclist and bicycle have a total mass of 68 kilograms. Calculate the energy of the cyclist and the bicycle. Use the equation. Kinetic energy is a half mv squared, m being the mass and v being velocity. So if we substitute in our numbers, kinetic energy is a half times the mass, which was 68 kilograms, times our velocity squared. And if we calculate that out, we get an answer of 4,900 joules. Then for part B, we need to describe the energy transfer that happens when the cyclist uses the brakes to stop. So here the energy transfer is going to be from the kinetic energy store from the movement of the bicycle being transferred into the thermal energy store due to the brakes and friction of the brakes on the wheels. Now for part C, the cyclist starts to cycle again. The cyclist does 1,600 joules of useful work to travel 28 metres. Calculate the average force the cyclist exerts. Now here we have to recall one of the equations that we were supposed to learn. So work done is force times distance. So work done is force times distance travelled. And if we input our numbers, so the work done here is 1,600 joules of energy, and that would be the force times the distance travelled, which was 28 metres. And if we rearrange our equation, force would equal 1,600 divided by 28. And when we calculate that out, we get an answer of 57 newtons. An athlete uses a training machine in a gym. The display on the machine shows the time spent on the machine and the amount of energy transferred during the training session. Figure 3 shows the display for two different sessions by the same athlete. Explain what the displays show about the average power of the athlete in each of the two sessions. So, first of all, if we remember, power is energy divided by time taken. Now, when we're looking at the two sessions, because the time taken is the same, we can see that over the same time period, more work is done in session 1 compared to session 2. And what this means is that session 1, there is more power in session 1, therefore, compared to session 2. A student has a bar magnet, a piece of iron the same size as the magnet, and some paper clips. Describe how the student could use these items to demonstrate temporary induced magnetism. So what the student could do is the student could produce temporary magnetism by using the magnet to pick up a paper clip. And the paper clip, because it's made from iron, should become a temporary induced magnet. So then the paper clip on the magnet could be brought towards some other paper clips and they should be attracted towards the paper clips, making a paper clip trail from the magnet in the first place. Then when the magnet is taken off the paper clips would no longer be able to pick up any other paper clips, showing that the magnetism was temporary. A student sets up the apparatus as shown in figure 4. When the current is in the solenoid is switched on, the solenoid attracts the iron nail. So describe how the student could use this apparatus to investigate how the size of the current in the solenoid affects the force of attraction between the solenoid and the iron nail. So the first thing the student do, they would note the position of the pointer before there's any current going into the solenoid. They would then use an ammeter to measure any current that's going into the solenoid when it's switched on. So they switch it on and they write down the reading on the ammeter to know what the current is. They would then have a look at the position of the pointer again and they would be able to work out what the extension of the spring was. Then they would repeat this investigation using different currents and they would be able to work out what the different extensions were with the different currents and be able to do a comparison. The spring constant of a different spring is 24 newtons per metre. The spring is extended from the unstretched length by 12 centimetres. Calculate the energy transferred in extending the spring by 12 centimetres. Use an equation selected from the list of equations at the end of the paper. So if you are able to look at the equation that you are given in the test, you will note that the energy is a half spring constant times extension squared. And if we input our numbers, so 0.5 times 24 times the extension squared, and we would get an energy transfer value of 0.17 joules. For question 4, we are given figure 5, which shows the vertical forces on an aeroplane. Use the information from the diagram to determine the size and direction of the resultant force on this aeroplane. So to work out the size of the resultant force, we would do the upwards force, which is the larger force, 8.4, take away the downwards force, which is the smaller force, 7.5, and that gives us a size of 0.9 kilonewtons. And because the larger force was in the upwards direction, the resultant force would also be in the upwards direction. Now for part 2, the aeroplane is descending. Figure 6 shows a diagram of the resultant vertical and horizontal forces on the aeroplane as it's descending. Complete the diagram to show the resultant force of these two forces. So to work out the resultant force, what we would do is we would work out our construction lines for the resultant force. So if I just draw them in as dotted lines there, and that would help me to draw the resultant force, and if I look at that, then that I can clearly see that my resultant force would be this one here that I am now drawing on a little bit thicker so we can see that. And it's really important that you put your arrowhead to show the direction of the force. There we go. The mass of the aeroplane is 750 kilograms. Calculate the change in gravitational potential energy of the aeroplane as it descends from 1,300 meters to the ground. Gravitational field strength, G, is 10 newtons per kilogram. So here is a recall question for the equation that we need to use. So the gravitational potential energy is mass times the gravitational field strength times the height. And if we substitute our numbers in, we have 750 kilograms as our mass, we have 10 newtons per kilogram as our gravitational field strength, and the height is 1,300 meters. And if we calculate that out, we get an energy value as 9,800,000 joules. An aeroplane is powered by an engine that burns fuel. The fuel supplies 6,500 kilojoules of energy every minute. The efficiency of the energy is 0.7. Calculate the power output of the engine and give your answer in kilowatts. So the first equation that we need to use is efficiency is useful energy output divided by total energy input. So if we substitute our numbers in, we will see that efficiency 0.7 equals our useful output divided by the total input, which was 6,500 kilojoules of energy. Now, if we rearrange that, our useful output energy would be 0.7 times 6,500, and that would give us an answer of 4,550 kilojoules of energy. Now, we want to work out the power. So the power would be energy divided by time taken. And here we had our energy as 4,550 kilojoules divided by 60 seconds. And so that gives us an answer, when calculated out, of 76 kilowatts. And we don't need to change it into watts because we were asked to give our answer in kilowatts. So that would be 76 kilowatts. In part 2, we are asked to explain why the efficiency of the engine is less than 1, so it's less than 100%. So the reason for this would be that the output energy is always going to be less than the total input energy, and that's because some of the energy always gets dissipated to the surroundings. So we would always have some wasted energy that is dissipated to the surroundings. A resistor is connected to a power supply. The potential difference across the resistor is 6 volts. Which of these corresponds to a potential difference of 6 volts? So 6 volts is going to be 6 joules per coulomb, and the only answer which corresponds to that would be answer C. Part 2 tells us that the resistor remains connected for a period of time. The current in the resistor is 200 milliamps. A total charge of 42 coulombs flows through the resistor, and we have to calculate in minutes the time taken for this amount of charge to flow through the resistor. So, first of all, what we need to do is we need to change the current from milliamps into amps. So we do that by having 200 milliamps divided by 1,000, which equals 0.2 amps. The equation that we have to recall is charge is current times time. And if we input our numbers, our charge, which is 42, is our current, which is 0.2 amps, times our time in seconds. Our time, therefore, would be 42 divided by 0.2, and our time works out at 210 seconds. However, we need to give our answer in minutes. So if we do 210 seconds divided by 60, that would give us 3.5 minutes. So our answer here would be 3.5. So for part 3, calculate the total energy transferred by the 6-volt power supply when a charge of 42 coulombs flows through the resistor. So the energy transferred is the charge times the potential difference. If we input our numbers, we have 42 times 6, and we should get an answer of 252 joules. The resistor becomes warm while there is a current in it. Explain why the resistor becomes warm. So the resistor is going to become warm because there's going to be collisions between all the electrons in the lattice and the actual lattice. This means the lattice is going to gain kinetic energy, and it's going to vibrate more, making it warmer. In part C, figure 7 shows a cardboard tube with a wire coming out from each end. So we've got our figure 7 there. There are two 10 ohm resistors inside the cardboard tube. A potential difference of 6 volts is connected between P and Q. There is a current of 1.2 amps in the wires. Deduce how the resistors have been arranged inside the cardboard tube. So what this means is we've got to work out, are the resistors in series or are they in parallel? So first of all, we know that voltage is current times resistance. So to work out the total resistance, we would have our voltage, which is 6 volts, equals our current, which is 1.2, times the resistance. So our resistance is going to be 6 volts divided by 1.2 amps, and this works out at us having a resistance of 5 ohms. Now, because we've got a total resistance of 5 ohms, and we've been told that there are two resistors which are 10 ohms each, that is greater than the total resistance that we need of 5 ohms. And we know that if we have resistors in series, then their resistance adds up. So if these two here were in series, our total resistance should be round about 20 ohms, which is not the case here. So that means the resistors are in parallel. Okay, and the key thing here is that we have our resistance in series, which should be 20, but when we actually calculate it out, it's only 5 ohms. So for question 6a, figure 8 shows identical filament lamps connected together to a 12-volt power supply, and they're connected in series. Calculate the potential difference across each lamp. So to calculate the potential difference across each lamp, it's going to be the total voltage divided by how many lamps we have. So it would be 12 volts divided by our 8 lamps, which means each one of them has a potential difference of 1.5 volts. Now for part 2, the power output of each lamp is 0.75 watts. Calculate the resistance of each lamp, and this is a 4-mark question. So here we are going to have to use two equations. Now the first equation we're going to use is power is current times voltage, and this will allow us to work out the current. Once we've worked out the current, we will then use our equation resistance is voltage divided by current to work out the resistance of each lamp. So using our first equation, 0.75 watts is current times voltage, which we worked out in the last question was 1.5. That means our current, therefore, is going to be 0.75 divided by 1.5. And if we work that out, our current works out to be 0.5 amps. Now we are able to use our second equation, because resistance now would be our voltage, which is 1.5, divided by our current, which was 0.5. And draw a line down there. So this was worked out here, and now we're using it here. And if we calculate that out, that gives us an answer of a resistance of 3 ohms for each of those lamps. So in this question, we need to explain with the aid of a circuit diagram the method a student could use to investigate the resistance of a single lamp, how the resistance of a single lamp changes with the potential difference across the lamp. So the equipment would need to be set up with an ammeter, a bulb, and a variable resistor in series, and a voltmeter positioned across the bulb in parallel to measure the voltage. So we would have to set up the equipment as shown in the diagram, and then we would calculate the resistance of the bulb using resistance is potential difference divided by current. So we would measure the voltage on the bulb using the voltmeter, we'd measure the current through the bulb using an ammeter, and then we would use the variable resistor to change the voltage of the bulb. Each time we do this, we would measure the voltage and the current to work out the resistance. And we would do this for around about 6 different voltages and the corresponding current values to work out resistance. We would then be able to see if there is a correlation between the resistance of the lamp with changing potential difference. This is the list of equations that will be given to you in the examination. So these are the ones that you do not need to learn. So these are the physics equations that you do need to learn. And this brings us to the end of this past paper. I really do hope you found this useful. If you did, please hit the subscribe button underneath. It will give you easy access to lots of past papers like this, not just in physics, but chemistry and biology too. And also you'll be able to access some topic learning on the different topic areas, biology, chemistry and physics.